Great. So thank you everyone for joining us for this week's seminar series. This week we have Guangya Yang presenting. Guangya is currently a senior scientist at the Technical University of Denmark. He received his PhD from the University of Queensland, Australia. And from 2020 to 2021, he worked full-time as a specialist on electrical design, control, and protection of large offshore wind farms at Ørsted. His current research interests focus on the stability and protection of converter-based power systems with an emphasis on offshore wind applications. So thank you, Guangya. You can now present.
Thank you very much, Daniel, for your introduction. Let me start share my screen. Can you see my screen?
Yes.
Okay, great. So good afternoon, everybody. I'm the most participant from US, and my name is Guangya Yang. I'm a senior scientist at the moment with the Technical University of Denmark. It's my pleasure to give this talk today to you on the transient stability assessment of offshore wind farms. We did a research project together with Ørsted, where we look at from nonlinear perspective of stability for offshore wind farm connections, because there's some motivation behind that. There are some events that cannot be analyzed or captured by linear analysis. So therefore, we started a project, research project 3 years ago or 2.5 years ago, where Suji he's my PhD student, and we together developed the methodology, look at the transient stability of the wind farm, typically from a converter, grid-connected converter perspective. So this presentation is mainly on one of the work that we did, that looking at the regional attraction for the grid-connected converter, and extended the energy function-based analysis from a static energy function to a time-dependent energy function. So, the agenda today, beginning, I will give a short state of art of the stability assessment for offshore wind farms. Currently, what is being done in industry, and the current the typical methods used, and then I will go a bit more into the reduced order model for the grid following control-based converter, and then we'll develop the nonlinear analysis based on that model, and also we present the proposed non-autonomous wind turbine model, and also the validation of the effecting of the non-autonomous wind turbine model in nonlinear analysis, and concluded by future research directions for this topic. So there have been a couple of cases in the past where there are stability issues related to Type 4 wind turbines. Type 4 is probably many of you know, is a full converter connected wind turbine, where the interface between the turbine and grid is a full-scale converter. And there have been both small signal and transient stability phenomena seen in industry. And there are two cases listed here. One is from Hami wind farm in Xinjiang, China, where they observed oscillatory stability of this wind farm, and at a subsynchronous level, where this oscillation also triggered torsional oscillation with a nearby thermal power plant. This is caused by controlled interaction oscillation or resonant with the mechanical torsional oscillation. And Another case is also recent, is from Hornsea 1. It's a very large offshore wind farm in UK, and this offshore wind farm is the install capacity is above 1 gigawatt. And there was a case in 2019 where this wind farm tripped from the grid and partially caused a blackout in the area where it's connected to. And that case was due to a lightning strike, and then followed the voltage dip. And afterwards, there was some oscillations between voltage and the reactive power due to and then the wind farm tripped due to poor current of the turbine protection. So this case is more seen as a transient stability phenomena, where the previous case is a oscillatory stability. As we know, like the wind turbine controls is mainly has many controls. In the grid side converter has a typical PLL, a phase local loop that treats the phase of the grid voltage, and then there's a voltage and reactive power control and power control, DC link control, and current control. And also at backend, you have this pitch control and then torque control, so on. So these controls are organized and then they are separated in frequency. So they are the bandwidth. There's no overlap among the in the bandwidth among these controls. And then when we look at the stability of the system, we can look at the different frequency of the stability, where the stability phenomena occur, and also link with the controls, the bandwidth, so that some controller contribute most to the low frequency or super synchronous frequency range, and some controller at harmonic range, and then some controls like PWM will contribute to a very high frequency range. And then polarized through control is a special control that is during fault is activated, and that control is contribute to near synchronous frequency because it follows the grid. So and if we can link these controllers to the stability and also frequency, then we could design the control, and particularly for that phenomena of interest. Currently, the stability assessment methods you can categorize in 3: time domain simulation, that is the most intuitive one that we develop RMS or EMT model of the wind farm, and then run a series of scenarios to look at the stability and polarized through capability and grid code compliance and so on. And then have a linear analysis. There are 2 methods: eigenvalue based and impedance based. Eigenvalue based, everybody familiar with, and then impedance based is also more and more used because of the black box model of the wind turbines that start to get a full state space matrix. So time domain methods. The developer will receive the models from suppliers and then put them together, connect them in a typically like PSCAD environment, and then run simulation. Of course, here like also some aggregation also needed for the plant side, and that should need to be validated also to some extent, but once you have aggregated the model that relatively accurate represent the plant level, and then you can run this model for example, for right-through analysis. And so this is the most accurate model obtained. And of course, it takes a long time to simulate. If you have a wind farm like about 1 gigawatt, you probably have to take a couple hours to simulate one case. And but typically, this kind of model is used for short period and transient analysis. Also, you can use it for energization and so on. That could present a quite big impact to the grid when you're energizing, for example, the offshore or export cable and so on. That is give a lot of transient to the grid. And the linear analysis is still the state of art for stability analysis. Here is the procedure where you have the PE model and then you linearize, and then you obtain the state space and do the eigenvalue analysis. And in wind farm, typically you have this models. You can obtain the linear model from manufacturer, and then you can link with all other models that you receive from other supply like StatCom and maybe other controller plant control and grid. And also you can put the model together and do the nonlinear analysis. And the good thing is that you can use it to trace the participation of the states in different modes, and then you can trace the root cause and then get supplier, different supplier to change the control, for example, who contribute to which mode, and then you can get specific. You can find the component that contribute the most and then change it. So that this is still the state of art currently used for stability assessment. For the wind farm, where you have a typical structure like this, you have wind turbines at the left side, and then you have this offshore substation, typically 2 or 3 transformers, depending on how big the wind farm is, of course. And then you can maybe have a passive filter, or maybe may not have this, but you have a reactive power compensation here, and then you have an export cable. And then onshore substation, you also have a filter, and you have and also reactor for compensating the reactive power, and also StatCom, and then external grid. When you do linear analysis, you need to look at both the grid operating scenarios, like strong grid or weak grid, so on, and also look at internal plant operating scenarios, like when you have a contingency case, -1 case, and so on, so that you can also capture the grid topology internal the plant, and then also the VTG control settings. So there's different mode for the wind turbine operate. It could be running as a PV or PQ, or different modes where you have a different controllers involved, and then you do linear analysis for all these scenarios, and then to check whether there could be any oscillating mode in this. But linear analysis, that already some limitations have been identified. That it's because linear analysis, when you have one model that is linearized, or you can validate it with a relatively, like most of current studies validate this linearized model of a component, and then look at the difference between the linearized and the nonlinear model. Typically, it's quite well captured the original model within the vicinity. But when you are scaling up this linearized model, let's say when you have a wind farm, for example, when you have a couple of hundred of wind turbines, and then plus maybe compensation device, some active controls. All this put together, the error start to increase, and some of the and also for large disturbances, then it's not possible to or not accurately reflected by linearized model. Therefore, the developer like us also start to look at nonlinear methods that could maybe used to complement the limitations of linearized model for large disturbances like faults. Another method is complementing the small signal or linear analysis is the impedance-based study, impedance-based method. It's a kind of a small signal method where you inject the certain frequency into the grid, and then you observe whether there's any resonance point for different frequency. So you develop so typically implement like at the PCC point, you inject the perturbed signal, and then you observe the current, and then you do the Fourier analysis, and then you can add the impedance. And if you have seen that if this converter and then grid impedance times together -1, then you have a unstable case based on this equation here. And then we did a small case study for wind farm where we did this frequency scan, where you can see that the group at a certain frequency there will be the magnitude they are matching, and then the phase margin is very small. So that means that you can have a certain case where you have a danger to be unstable. And when you increase the length of the you increase the grid impedance, you can see that also the phase margin getting smaller and smaller. So that's also validating that in a weak grid that you have a more less stable case. For impedance-based methods, it's advantage that it's flexible, that you can inject both positive and negative signals and then look at the system from ABC domain. But it's difficult to provide more insights when you look at the plant level. It's hard to figure out which device contribute to which frequency or which impede. So it's not that easy to as straightforward as a linear analysis that tells you the participation of the controls in these different frequencies. Come back to the transient stability analysis. Transient stability has been a topic studied for decades in power system, and typical methods like equal area criterion, extended equal area criterion, and energy-based methods. And with the grid following contour of the converters, the transient stability converters are mainly dominated by the following factors, like the phase locker loop, because transient stability is mainly looking at the near synchronous this frequency range, where phase locker loop contribute a lot in this frequency range. Therefore, like we look at transient stability, phase locker loop dynamics is very important. And then another contributing factor which may not be so much talked about is the grid code requirements. And we see that in our studies where the different grid code requirements actually have impact on the transient stability of the converter, because during the fault there are control switches from the far right through, whereas there's a grid code requirement of far right through, and also after the fault here when there's also grid code requirement on the ramping up the active power, for example. And those requirements are actually impacting the starting point of the turbine after the fault, because it depends on those controls. Controls will drive the operating point to a different area, and if depending on the requirements, and it has actually impact on the transient stability capability of converters. And also grid impedance of the fault also has play a big role in the transient stability. And later in the study will show that how grid impedance also is part of the equation for the stability margin of the converter. So for the reduced order model of a grid grid connected converter, we are using the current injection model to represent the grid side converter. So the grid side converter, you can you can see it as a current source, where the current inject from the grid converter has both an ID and like a DQ axis, and then the phase is tracked by the phase locker loop, and then there's then when it's connected to the grid, you can have a D axis circuit and the Q axis circuit based on this model, simplified model. And this simplified model only considers the PRL dynamics. The states only have PRL, where if you have a state synchronous reference frame PRL, then normally two states are of question. There's a PI controller, and also there is an integrator. So only two states for this in this model. And then when we look at the DQ axis, we separate the DQ axis of the converter side and the grid side. So converter side DQ and then grid side DQ has a in steady state there will be no phase displacement, because they will be the converter and then grid will be sync. But if in a dynamic situation there will be a phase displacement. Let's see when there's during dynamics the converter trace the data, the phase will be different than the grid, the synchronous reference phase. So there will be a difference. We call it data DF here. And then you can do this mapping between the grid side and then converter side values and DQ axis based on this phasor diagram. And then you can also establish the equations for this DQ axis. We are typically interested in Q, because Q axis is where the PRL is tracing. So the Q axis circuit is used for the analysis. And if we have the theta DF represented by this, this is the PRL equation here. This is the PI loop that this theta DF is basically here, and then you have this. This is the based on the Q axis circuit, you can establish an equation like this, where you have with PCC Q, the converter side, represented by the grid voltage, and then there is a phase displacement between theta DF and theta grid, and then you have other parts that the voltage drop at the Q axis, and also there's ID component participation here. So this equation is established based on this circuit, and then once we put this PVPCCQ expression into this equation 1, we are able to get a dynamic equation in this, where we're similar to to swing equation as a synchronous machine, but the difference is that it is nonlinear. You can see this coefficients of this equation are nonlinear, and then this delta dot is theta df minus theta g, and this double dot is like omega, and then here this equation m is if we resemble the synchronous machines swing equation, this it's in converter system is represented by this expression where the kp is the pi controls that this proportional gain, and the ki is the integral gain of the pi control of the PIL, pi loop of the PIL. And then you have also some the IQ, the ICQC, the converter, I access the Q current, and then ID C is a converter's IP access current. And then you have this is the full expression for this dynamic equation here. And for synchronous machine, the damping is constant, but for converter system, as you see, it's also represented by an expression which is nonlinear. The converter control during fault. So there are a few control switches after the fault take place. So first, the converter voltage, once it drops to 0.9 per unit, the converter is then running into a full ride-through mode. In this full ride-through mode, there's a certain critical requirement where it requires the converter inject the reactive current based on take a group like this, where this K factor could be from 2 to 10, and then once the voltage drops to a certain level, then the converter should inject 1 per unit reactive current. And there's a small room for still in the current limit, then the rest will be used for active current injection. And then after the fault, that means when the voltage is back to near 0.9 or also, that's also required by the grid code. Then this converter will be back to the normal operation range. And in the normal operation range, converter is running on the PV as a PV bus. So it's a control the active power and also the voltage at the terminal. And when the converter back to that mode, that then because during full ride through, the reactive current is prioritized. Active current is quite low typically, and then in this after the full ride through, this the control switch back to the normal operation, then this active current need to be run back to the previous setting, and there is also grid code requires that how fast this ramp rate should be, yeah. So these are the control switch that could take place during the fault, and as I previously mentioned, that this full ride through requirement and also this ramp rate after the fault implies also the transient stability of the converter, where we'll follow some analysis, more detailed analysis based on the model here we developed. So for transient stability from converters, initially you have a stable point, and then you also know there will be a stable post-disturbance equilibrium. And the main problem for transient stability is that whether the system after the fault, where it's XF, is able to transit to the stable equilibrium point. if this XF is outside of the region of traction, then you will go to the unstable case. Of course, like this is a quite ideal case where you have the region of traction is here, and then the system is autonomous and also doesn't have any extra energy coming from outside. Then you are naturally evolve into a stable equilibrium if you are if your starting point is within the region of traction. But if not, but for converter system, there are several conditions that the system can evolve to the stable equilibrium, because it's nonlinear equation represented than the second order system. So it's not autonomous and also time varying because of the controls that push certain so this coefficient in this model, they are not completely constant after the fault. Therefore, like it's a time varying system, second order time varying system, where we need to look at both the control and also the grid in order to determine whether the system can be stable or not after the fault. Here is just a case that to show how to evaluate the transient stability of the code. One time do the time domain analysis and then looking at okay, if I implement this ramp rate and if I implement this fault return the voltage after the fault during the fault, and afterwards whether the system can be stable or not. But this is just a case where we're developing Simulink with a more detailed model where it shows that, well, there's a certain voltage level dip, let's see, dip to 0.1 per unit, and with a certain control implemented for the rise through, and after and also the ramp rate of the current. Then after the fault, then the system at a certain point could lose stability, and then at a certain voltage like is stable. But this is just an empirical way of analyzing the system. If you do this in this, you can also use a bit more analytic way to analyze the system, like to estimate the region of attraction, as mentioned, where this for the second order system represented before, where you can have this two-dimensional plot that shows the region of attraction. So after the fault, you have the delta and delta dot that could start with a certain point where, and you start to and you put the certain parameter settings into the model, and then you do the in-time integration, and then you can, if you do a lot of times at a different starting point of within this two-dimensional plane, you are able to estimate the whole area of regional attraction for such a second order system based on certain assumptions of the parameters. Let's see, the grid side parameters like resistance, reactance, and the converter control parameters. So on, you can estimate the full regional attraction. So for the previous model, if we follow that line of study, let's say we assume certain parameters are constant, and we are interested in after the region of traction after the fault is cleared, and then to see the system whether it's within the region of traction or not, and analyze the size of the region of traction of such a system. Assume the parameters are constant. For example, this R and L of the grid as we know, and then this ID, for example, ID converter, this is assume that these are constant. That means that after the fault, when the control switches, you have a constant ID. That's kind of, let's say, during the fault, you have a low ID. After the fault, you have a high ID. But we are interested in after the fault, how system evolves, then the ID will be a kind of give a step change to the ID. And the IQ, you can, after the fault, you can have give a constant value, or here as IQ, in this study, we didn't do, we didn't very much, but in practice, this IQ and ID, they also, because the IQ will ramp down, the ID will ramp up, and but this ramp, because the after the fault, the converter is running at the PV mode, so the IQ is also follow the voltage, and but there's really future work that we look more at IQ dynamics, but for this system, if we assume that we know these values, and then this system can be simplified into a nonlinear, because we still have a sine cosine here in the T, this electric torque and then electric torque and the damping term. We still have this sine cosine functions, but it's autonomous, because then these values are all constant, and then based on this, we can analyze the TE equals TM at the equilibrium point, because then at the equilibrium point, this x2 dot will be 0, and then we can look at TE equals TM and then calculate the x1 here, the value of x1 here, and then look at the equilibrium point, and then once we put this TE equals TM, we can say sinus x1 equals, yeah, this term here divided VG, and then you get 2 points of equilibrium point for this this is a V delta curve, because of TE is TE here is a V times sine, so it's now it is different than the synchronous machine, which is the P delta curve. Now it's the V delta curve, and in this case here we can see there's 2 equilibrium points, theta 0 and theta max, and this one theta 0 is a stable equilibrium, and this is a non-stable equilibrium. And in order to have a valid point for the for this sign, because this sign, this value eta here, it equals this value, and this value need to be less equal than 1, so that we have a legitimate this function value. So in that case, that we need to constrain this less equal than 1. But this less equal than 1 means that this value here is dependent on the, let's see, ID, and then this omega L, and also IQ and R. I assume R is very small, so at least it's determined by ID and the omega L. And then if you have a really high ID and a weak grid, large omega L, then there could be a case where this eta large equals than 1. Then in that case, you don't have an equilibrium point. That means your curve TM or TM and TE cannot find a intersection point. And in order to have an intersection, that means this has to be less equal than 1. And then you can have this condition established. And you can see here that this grid impedance here does play a role when for the steady state equilibrium. And both during the normal and fault condition. During the fault, you have a V, because the V will be reduced, and then you have a reduced V sine delta curve. And in that curve, you have, if you set a unrealistic ID, then you can also have a problem that you don't have any equilibrium point that you can find. And now look at the damping term of this autonomous system model. And the damping term is according to theory, is desirably positive for system stability. But it's not, of course, it's not a sufficient condition for system stability, unless it's a Hamiltonian system that is, there's no, yeah, it's autonomous, and also there's no then there's no energy exchange and so on with others, and then in that case you have a kind of a guaranteed stability of the system. And when we when we look at this equation here, we could also see that this damping is dependent on this x1, that is the delta, and then this delta you can see is the PLL trace phase, and then the grid phase, voltage phase, the phase difference. More or less, you can see as these two differences. And if this is wide enough, then you have a better damping. But well, this is small enough, you have a better damping. If it's wide, then you have, because it's a cosine curve, because then you are, when the x1 goes higher, that means the PLL lose the trace of the phase of the grid, then you have a less damping. And here is the this term is also again like determined by the grid side reactance, and also this ID that is a reference active current that you give to the converter. So when you give higher active current command, then this damping term also start to reduce. And then when this x1 increases, also this damping term reduces. So, and we have seen that in a simulation that this damping term can be both positive and negative for some period, and then, but it's not guaranteed that even it's negative, it doesn't mean that system is unstable, because it's a nonlinear system. And then even it's positive doesn't mean the system is stable. But still, like from general perspective, it would desirable to be positive so that the system is stable. And then if we look at this term and then plot the damping curve, you can see that if you have a higher ID, basically that the positive side of this cosine function, of this cosine wave, will be reduced, because you have a constant here that is bring the curve down to the negative side. And that means this delta mean and max will be reduced if you look at the positive side of the curve, of the damping curve. And here, this figure, it shows that this is the positive side. That this for the you remember here in this figure, it shows that these are the stable equilibrium points, and then this is the unstable equilibrium point. And then in between here, these two, you have a region that you have a positive damping region, that this term is positive. And then you have also a region that when you are closer to this side, you have a region that is negative damping. And in the dynamics, this trajectory of the system could start from here and then goes to here and then back, and maybe back or maybe not back. But it could also happen like it goes in and out several times and then still stable. That's what we have also seen. So if we look at this autonomous wind turbine model and then try to develop the energy function on it, assuming the constants or the coefficients of this of this two-order system are second-order system are constant, then we are able to develop an energy function just like a synchronous machine. And we apply the equation that used by synchronous machine, when we can get an energy function. And then for this energy function, for the sufficient condition, the derivative of this energy function should be negative. And then if we take the derivative of this, we get this one here. And then as x2 squared is always positive, then this is the damping term that has to be positive in order to have this value less equal than 0. And if we give this condition to this, so let's look at the boundary of damping. Then we can see have the damping equal 0, and then look at what could be the xy, that is the delta, that value. Then we are able to get the boundary of the delta. And then within this delta, we have positive damping, and outside this delta region, we have a negative damping. And this is the analysis we can do here. Is just an example where if you use this condition for the damping, then you get this boundary here, and then you have so these are the energy level set that you develop based on energy function, where on this curve you have the same on the same energy level. And if you have positive damping, that means if you start from here, then the system energy will get dissipated to 0 over time. And then if we based on this this region defined by the delta, then we are able to see, okay, this is probably the most conservative region of traction that we can determine for this autonomous system. And of course, it doesn't mean that outside here this is not stable, because if you use equal area criterion, you have a larger ROE than this one. But here it is the most conservative estimation of the ROE. And this is a sensitivity assessment of the ROE, where with respect to different grid parameters and also damping level. So at a higher damping, a strong grid, this gray area here is a theoretical ROE down by time by many simulations, time-bound simulations to that identified area. And then if you use this damping and then looking damping boundary with positive damping, you can identify that this is the ROA based on the damping positive this condition. And when you have a high and weak grid, you can see that this theoretical region of traction also reduced when in a weak grid condition, and also the regional traction identified by the damping boundary condition is also reduced. And then if you have a low damping and strong grid, you have this term. But this is basically to show that when you have a low damping weak grid, you have the smallest regional traction identified, both the theoretical one and also the identified one, estimated one, using the damping conditions. And come back to this nonlinear, non-autonomous regional traction. This is an example to show that when you have if you don't consider the run, and the system you identify, you do the analytic model and then do the integration, give a step change to the ID, the system maybe show that it's unstable, but in reality there is a run in the ID, converter ID. Therefore, like if you put that condition in, the system could be oscillating and back to the stable equilibrium. Therefore, that means that in the fault recovery period, if you don't consider the ID run, you probably get a very small region of traction estimated, which is maybe not realistic. Therefore, like you need to consider the ID when you analyze the stability. And then for this, if we consider that ramp rate of the ID, then the previous equations need to be revised, given this ID term previously as a constant, now become a linear function of the time, and then there's a ramp rate that is determined that is given by the grid code requirement, and then you have a modified set of equations for such a system. And for this system, there is a method that you can develop energy function for such system if you can map this equation into this type of equation, where here this equation, let's see, this u dot in our case is delta, and then this is the damping term, and then this is like this electric torque, and this is mechanical torque, and here this is the omega or delta double dot. And if you do this mapping to this from here into here, then you are able to derive or formulate the energy function based on this equation here. I will not go more in detail, but you can find it in a paper that we are writing, and then this is the mapping result. So this RT you can map as like M, and then this phi function can be mapped as like this, and then R dot T plus phi is the damping term, and then we have also the electric and mechanical torque mapping from this non-autonomous representation. And then for energy function, we can also formulate the terms used by the energy function here to formulate this function here. And then we can assume that we can then look at the stability of the system, looking at this differential derivative of this energy function to see if it's stable or not. And if we take the derivative of this energy function, we get this expression. And where the RT is positive, is a positive because it's given here, and the exponential function is also positive. Then the question is this phi. So this function here, whether this is positive or not, that will dictate whether this energy function this derivative is negative or not. And if we have the phi equals 0, and then to look at the boundary of this this derivative of the energy function, then we can have another estimation of the region of traction, which I think is bigger than the previous one with an autonomous system, because now we have the ramp rate and included the effect. And then once we have this ramp rate included, then this boundary of the phi will change, or this delta will change, and then that we have effectively a larger ROV. So here is when we take a different ramp rate in the study, we can see that when you have a different ramp rate, then this is the real ROA done by many simulations, and then this is the estimated ROA based on the condition with phi equals 0. we estimate the ROA here. And then with another ramp rate, you can do the same. And then you can compare the size of the ROA based on different ramp rate, where you can see that when the ramp rate is low, actually the ROA is high. That means that when you have a higher ramp rate of the active current, actually the system stability is worse because you have a less smaller ROA. And that is also something that the grid code maybe didn't consider, that from nonlinear stability point of view, that when they would like to have the active power goes back to normal as soon as possible, because during full ride through, if you have a lot of converter in the system, for example, if then the active current is low and the reactive current is high, and after the fault, if then to keep the system frequency stable, you would like to have a higher active current back to normal. But this high active current could also drive the system to an unstable region. So here is a verification of the ROA of just compare from autonomous and non-autonomous representation, where a autonomous representation of the system of the wind turbine case, where you estimate the ROA is this size, and then when you consider the non-autonomous system, you have a larger ROA. That means that you have a wider, let's say, a stability boundary that you have in the system. But as said, that when you have a different ramp rate, then this ROA will also change. And in fact, this ROA, the boundary is also, once you have a time, when we have the time as a variable in the expression of the energy function, so on, this ROA also become a function of time. So initially you have a very large ROA, and afterwards, like with the time increase, the ROA will become smaller. But it doesn't matter so much, because as long as the starting point is within this initial ROA that is a lot wider, then you are able to you have a higher chance to get into a equilibrium point. So here, this is just from energy perspective to see how fast the energy dissipated. This is for non-autonomous system. For non-autonomous system, this is for non-autonomous. Just follow the previous case where the different ramp rate is used, and for higher ramp rate, the energy is dissipated faster from the energy function value. But of course, I will say that the stability of the system is worse in this case. Here, in this case, when you have a ramp rate is low, of course, then this energy function doesn't, the energy doesn't dissipate as fast as when you have a higher ramp rate. However, you have a better ROA for the system. So, looking at the future stability, we see like we need right now we consider the ramp rate as this nonlinear block in the control, but also there are other like saturation need also to be present in the model, so that you have a more realistic case. Because we see that with this nonlinear represented in the model, typically you have a better ROA represented, and there's also an ongoing work that we're trying to include this saturation also in the model. And because once you have saturation, then you have a certain value, like the starting point of XF is then fixed at a certain point that you have you're limited that value, and then that has better. That means that you have better chance to that XF is within the ROA that the system has, and then yes, the parameters that the coefficients of the nonlinear model, the second order model, need to be expanded to reflect the control switch more accurately. Because I said that there will be, once the control switch, then you have also reactive current, active current that follow different paths, and that should also be reflected more accurately by the model. And for the plant level, so far we talked a lot, but they're still at the single converter level. But with the plant level, we need to see how this model could be representing to the plant level. Aggregation and validation is needed here. That's also something that we are trying to do. And we also see that for in future that this mixed nonlinear and linear models assessment method could be better for could be developed for this plant level, because the nonlinear part, maybe the converter control, so on, is very nonlinear. There are many nonlinearities here, but there are certain components where it can be represented by linear model where there's no much, for example, this control switch and so on, and they're not limited or defined by the grid code, where you can use a linear model to represent. Then you have a mixed simulation for both nonlinear and linear models together. And then just a little bit about the time domain. So as we have right now, like time domain method, like offline studies is concentrated on p-scared and peak silence study. At least in Europe, is peak silence used. Maybe in the US is PSSE, and maybe some other countries use other tools. And we also have in a real-time simulation that we are also trying to set a benchmark system or test system for the wind power plant testing, because there is let's see, we have more multi-wind in future, have multi-wind HVDC and multi-wind wind farm. So on these cases, as we need some real-time simulation to validate, because to make a model offline running together could be too slow to evaluate it when you have a very complex system like multi-wind HVDC and wind farm. Therefore, we also in IEC started working on item like -21-5, where we look at the test system, benchmark system for wind power plant testing. So to conclude, we see that nonlinear analysis does actually help to better understand the stability of the power system that is beyond the linear domain that could tell. And right now we of course use the second order model still, but still we see that there are certain insight that can provide also based on this second order model. The plant level study, of course, is another complexity, and requires more aggregation, model validation, so on. That's where it will be where we are also trying to look at how to expand the current model for more converter system. So that's all my presentation. Thank you very much for your attention.
Thank you, Guangya.
don't know if any questions to this or.
I think Maria has some questions. Or we can go to Zoom.
Are there any questions online? Nobody here.
No, yeah, you can ask questions.
Anybody here? So I'm just wondering, can you hear me, Guangya?
Yes.
Okay, so you made a case somewhere halfway through that these onshore wind power plants are really just like second order conventional power plants, right?
Yes.
Yeah, and then apply the Lyapunov and all these other things. So how are they really different? How do you see what's sort of unique about onshore wind power plants that is sort of operating and analysis purpose that we have more than if you have conventional controllable power plants or onshore plants? Is there any difference, or because your title was offshore, right?
Yes. Yeah. I see. Yeah. It depends. I think offshore, of course, like it's more. Let's say you have the export system, where onshore wind farms doesn't have, and for offshore, we also like see that. Well, if you look, there's an offshore substation, and then there's offshore substation. This 100-kilometer, typically like couple tens of kilometers at least. This cable that separate the two systems. So electrically, you can see, okay, offshore, kind of, you can take offshore separately. So that offshore system from offshore substation to the wind turbines, you consider as a one system, as a like a plant, or kind of just VTG dynamics that dominate that system at offshore. And then onshore, you have for offshore power plants, you have onshore side, you have a lot of compensation, you have also STATCOM and so on, other active control equipment. And so this equipment here, like they have basically for grid code requirements and so on at the plant level. And where you, for stability studies, you can probably take the offshore side just separately, say that, okay, we do not look at onshore because onshore they have other devices that is affecting the with the interact with the grid, but you can maybe aggregate this export cable to and onshore substation to the grid side, and then look at the offshore side, because then you have a relatively simple like setup that we have only VTGs, and then there is a possibility or chance that you aggregate these VTGs together, or at least to some extent develop studies like this. And then for onshore wind farms, where you can, in a way, you can do the same. But for onshore, probably they depends on where you connect. You probably connect to distribution grid directly instead of transmission grid. For offshore, it's a large plant, typically of large plants where you connect to a higher voltage, at least sub-transmission level. Or maybe you can, I've heard that in the US, some areas like this, you can connect to low voltage, lower voltage, mid voltage, distribution grid voltage level. But typically, it's high voltage. And
how about the DC link? DC link also between the offshore and the onshore. What difference does that DC link make at the end? Does it make a lot of difference or no?
DC link does actually make a difference. Yes, DC link also contribute to this to the transient stability. Like this frequency only 50%. This is also something that we need to see how to include the DC dynamics also in the second order system, which is missing right now. We consider that as a kind of constant voltage, but it does like the DC link protection and so on. There are also like the impact on the VTG stability. Yes, it does impact. Yeah.
Okay, thank you. Any questions on the online people, remote?
Yeah, it looks like Lin from EPRI has a question.
Please go ahead. Can you read the question or state it, Lin?
Oh, can you hear me okay?
Yes.
Okay, yeah, thank you for presentation. I just have one quick question. You know, I remember in your presentation, you mentioned the grid following inverters.
Right.
I'm wondering if you have considered like a grid forming inverters in your transient stability analysis. Yeah, that's my question.
Yeah.
Yeah.
That's a good question. Actually, grid forming inverters, like it's the control of grid forming is closer to synchronous machine compared to grid forming, and in that case, the second order representation is you can also use, I believe we haven't done that work yet, but I believe that you can also develop the second order representation for the grid forming control. Of course, with a different set of parameters, maybe that also expression of this parameters, and we also did some transient stability for grid forming, where we look at all the current limit that during the fault that affecting the stability of the converter. So you can lose phase of the grid voltage phase during the transient during the fault because of current limiting. Where with the grid following, you don't have this issue because you have the PLL that keeps tracing. At least it helps to trace the grid voltage, even though you have a current limit and so on. But with the grid forming, you don't have PLL, so you could have loose trace of that synchronization is based on active power, following active power, so we did some little bit of study on how you could compensate this loss of trace of the phase during the fault for grid forming. Yeah, but I mean the studies here, like in this presentation, I believe you can also develop because we look at after the fault. So after the fault, XF, that's also dependent on the starting point, also dependent on the still like right now the grid code has not been developed for grid forming, but they will soon probably start more and more requirements, and then I believe that similar studies can also be applied. Yeah.
Okay. Yeah. Thank you very much. Yeah.
Yeah, I think that's all the time we have for questions.
Thank you very much, Guangya.
Yes, but thank you, Guangya.